In this video, we're going to be going over your review assignment, which is from chapters 22 and 23. In chapter 22, we're going to look at problems 31 and 65. And in chapter 23, we're going to look at problems 79 and 80. So first off, number 31 gives you a picture of a metal bar. So I'll draw the metal bar here. And it's being suspended from two strings. And there is an angle between the vertical and how the string is kind of hanging right now. And what they want you to find is that they want you to find what angle this actually is. So first thing, they have labeled on here that the weight, kind of a free body diagram, is pulling down, and that the current is going to the right here. And if you go ahead, and then it's in a magnetic field, label B there, that's going down. So if you use your right-hand rule and your thumb goes in the direction of the current, and it's hard to do in this video, but your fingers point down because of the B field. If you imagine, your palm is going to point into the page, which means your magnetic force is kind of into the page like that if you think about a 3D picture. So then it's just a kind of situation of static equilibrium where the Y component of your tension, if you think about this as your string right here, so this Y part of your tension, which I'll label tension and the Y, has to be balanced out by the weight going down. That's tension. And your X part is kind of going in and out of the page, and that part of tension has to be balanced out by the magnetic force that we just determined from that direction there. So in order to find the angle, the first step that you need to do is use this Y side and say tension in the Y is equal to M times G. And then knowing that this angle right here is theta, you can go ahead and say that T times the cosine of theta is equal to M times G. And therefore you get tension to be equal to mg divided by the cosine of theta. Step number 2 then is to use your X components and say tension in the X is equal to your magnetic force. And since we have current going through a wire here, your magnetic force is going to be B times I times L. And so what we will get is your tension in the X is going to be, in this picture, T times the sine of theta equals B times I times L. And then we know from above that tension was mg divided by the cosine of theta. So plugging that in, we get mg divided by the cosine of theta times the tangent of theta equals B times I times L. And knowing your trig functions, sine over cosine is the same thing as tangent. So you get mg times the tangent of theta equals BIL. And finally, you can solve for theta to be the inverse tan of BIL divided by M times G. And you could have technically done that in one step, just using your tangent function if you wanted to. Next one we are going to look at is number 65. And number 65 gives a picture of two parallel plates here. And the parallel plates are in a magnetic field that is going into the page, something like this. And a little proton is entering at a certain speed here, okay? And they want to know in part A the magnitude and direction of the electric field in order for it to go straight through. So this is one of like those velocity selector type problems. So if you think about your little particle when it's in between the plates here, according to your right-hand rule, if your velocity is going to the right and your magnetic field is going into the page, that means that this little particle is going to experience a magnetic force going up. So that is your force from the magnetic field. And if you want it to go straight through, that means it has to be balanced out by an electric force going down. So if you think about your little particle in there, you've got FB going up and you've got FE going down. And in part A then, your key is that you want your magnetic force going up to be balanced by your electrostatic force going down. And so for a little particle, your magnetic force is B times V times Q. And that's going to be equal to your electric force, which is E, the electric field, times Q, the charge of the particle. And you can see your Q's will cancel, and your electric field then will be B times V. And they tell you that the magnetic field is 0.52 Teslas, and the velocity of the particle was 1.42 times 10 to the 5th meters per second. And so you can get an electric field of 73,840 newtons per coulomb. And then for the direction, you've got to think about, go back to your free body diagram here. A positive particle will always be forced in the direction of the electric field. Therefore, your electric field must be downward direction. Part B then wants to know, suppose the electric field was produced by a plate separation of 2.5 meters. What is the potential difference between the plates? And for that, you can use V equals E times D, where we are solving for the electric potential. We know the electric field from above is 73,840, and the distance between your plates is 0.025 meters, and you get 1,846 volts as your answer. Finally, for part C, in order for this to actually happen, the top plate of your system here, if you think you've got your little positive particle and it's experiencing an electrostatic force down, your top plate has to be positive and your bottom plate has to be negative in order for that to happen. Alright, so finally we are going to be on chapter 23, and we are going to start with problem number 79 here. And 79, I'll kind of draw a picture. We have a resistor and a rod going across these two rails here. And the rod is falling downward initially with a certain velocity v. And the rod has a length L. And the whole system is in a magnetic field that is going out of the page, kind of like that. So A wants us to describe the motion of the rod. So initially, when it's released, the rod is just going to be in free fall, and it will start falling downward. But you'll notice as it does that, as the rod falls, the magnetic field going out of the page in this top loop here is going to start increasing. And so as a result, Mother Nature, if you will, is going to induce a current to kind of counteract that. And so if magnetic field is out of the page is increasing, she wants to create a current to produce a magnetic field into the page. And so there is next going to be an induced current, and that induced current is going to be in the clockwise direction. I'll draw a picture in here. Because that way, if take your right hand and your fingers curl in clockwise direction, your thumb points into the page, and that's what the induced current is going to look like. And so at that point, at some point then, with the current going clockwise, if you think about your other right hand rule, and you take your thumb and it's going to the right, and then your magnetic field is going outward, your palm is going to point upward. And so the next kind of thing that's going to happen, and all this is going to be kind of simultaneous, is that there's going to be an upward force produced on the rod. And so the result of this is at some point it's falling down due to gravity, and there's an upward force due to the magnetic field, and at some point the fall of gravity, or the force of gravity going down, is going to be balanced out by that magnetic force from the induced current, and at that point the acceleration of the rod will approach zero, and it will just start moving at a constant velocity. And it will continue moving downward because according to Newton's first law, it was already in motion downward. So it's going to stay in motion, it's just that your forces are kind of balanced. Now B, I think we have already answered, but that asks for the direction of the induced current, and we said it was going to be clockwise. And then finally, part C wants to know the speed of the rod after it's fallen for a really long time. And that's when your forces are going to be balanced. So we'll have FB equals FG. And our FB is going to be Bill times the sine of theta, but I'm going to leave out sine of theta since the magnetic field is perpendicular to the plane of the loop there. And so we'll get BIL equals M times G. And in order to find the induced current, we'll have B, it's going to be equal to the induced voltage, V, divided by the resistance of the circuit, R, times L, equals M times G. And if you rearrange stuff a little bit here, we will go ahead and get B, my pen's running out, BVL over R equals M times G. And finally what we can do is plug in for our induced voltage there, and we know that is going to be B times L times V divided by R times L still equals M times G. And the result, if you finally solve for velocity, is that the velocity can be R mg divided by B squared L squared. And again, I kind of shot over it quickly, but this right here came from the idea that we know our induced voltage is negative change in flux over change in time, and we kind of simplified down that down to the equation BLV. Last one that we need to look at here is problem number 80. And problem number 80 has a magnetic field going out of the page. And in that magnetic field is a loop that is moving to the right, and it has a length of side L. And so, and then I guess in the other side here they call W for width. And it's moving to the right, and so in A we want to find the rate of change in the magnetic flux at different points. So you got to understand what they're asking for here is the rate of change of magnetic flux is your change in flux over the change in time, which by definition is your induced voltage. And so in part A, just before the rod enters the zero field, so while it's all still in here, notice the magnetic flux isn't going to be changing at all when the rod is still in your magnetic field. So in part A, as long as the whole loop is in the magnetic field, your induced voltage, or your change in flux over time, is just going to be zero. Now, in part B, it's asking when it's entering your zero field. So when some of the loop is outside the magnetic field and some of it is still in, according to that, your induced voltage is going to be B, the magnetic field, times, we use the idea of L times V. But if you look to the specifics in this problem, your B is your magnetic field. And the L here refers to the length of the loop that stays consistent throughout the magnetic field. So in this case, it's actually W. So we get BW times V, which was the speed of the loop moving out of the field. Part C then, once it is fully within the zero region and your loop is out of the magnetic field, you will have zero induced voltage, because again, there's no change in flux at all, so there isn't an induced voltage or current. And then finally, part D is asking, for each of the cases A, B, and C here, talk about whether the current in the loop is clockwise, counterclockwise, or nothing at all. So in parts A and C, when there is no induced voltage, there is no induced current. And so you will have, I'll just say 0, or there is no current. But in part B, if you look back to your picture, As the loop exits the field, there's going to be less magnetic field through the loop going out to the page. So Mother Nature wants to induce a clockwise current, if you think about your loop here. So, or sorry, I meant to say counterclockwise. A counterclockwise current, just like that. And so then if you take your fingers and curl them counterclockwise and your thumb comes out of the page, that will kind of counteract the loss of magnetic field due to the loop moving right. And so the result is that in part B, there is going to be a counterclockwise current induced in the loop.